When we graph the truth set of this equation, read x is greater than or equal to 3, all we're really doing is putting a point on every spot where I can put a number in for x to make it true. For instance, can I put in 5? Is 5 greater than or equal to 3? Well, it is. So I put a point on 5. Is 8 greater than or equal to 3? Put one there. Is 1 greater than or equal to 3? No, it's not, so I don't put a point there. Is 3 greater than or equal to 3? Yes, it is, so I put it there. What about the numbers in between? 6.5. Yep. If you think about it, you're going to have to shade all of them. And then, what about 102 that's not even showing on the picture? Well, we'll have to represent that also. Well, what we do is we put an arrow. Okay? So this is what the picture looks like, or the graph, of all of the x's, or all of the values that are greater than or equal to 3.
Direction unclear. Please repeat request.
Let's try and cover all the points that make this true. And this is only x is less than 4, not x is less than or equal to 4. Is 5 less than 4? No, we're not going to put a dot on there. Is 2 less than 4? Yes, it is. Is -1 less than 4? What does it mean to be less than? It means to the left of. It sure is. Is 1.25 less than 4? It sure is. There's going to be a lot of them. Now, wait a minute. Is 4 less than 4? Well, it isn't. So I'm not going to put a dot on 4. So what I do is, there's numbers way closer to 4, like 3.9, that I do have dots on, but I circle the 4 to show that I'm going to get very close to it, but not include it. Now, -12 is not showing anyway, but I have to represent it. I'm not going to put a dot way out there. We know. And I have to put that arrow to show all the numbers that are less than 4. So in summary, if we have a greater than or equal to, or a less than or equal to, that means we want to include the endpoint. I hope you know we're going to have a solid circle. But if we have a less than or a greater than, and we don't want to include that endpoint, how do we represent that? With an open circle. Okay? Now, how are we going to graph something like this? We want all the x's that make both, there's really two statements here, both statements true. One of them is, and we're drawing a picture of x, so we're going to read x first here. You could say 0 is less than x, but I'm trying to draw a picture of x. So I'm going to say instead, x is greater than 0. The mouth's opening up to x, isn't it? So if 0 is less, x is greater. So I need all the points where x is greater than 0. That's going to look like that, isn't it? Now I have another statement here. Once again, I'm drawing a picture of x. So I want all the x's or numbers that are less than or equal to 5. Now I want to include the 5 in that case. Now what I want to do is get all the points that are both blue and green here. Both. What's going to be the final result? That's the graph. So the graph of the truth set of this conjunction, it's called, x is greater than 0 and simultaneously less than or equal to 5, is going to be, I want to call it a barbell. It's going to look like that. Note that there's a circle on the 0 because we don't want to include that, and there's a solid dot on the 5 because we do want to include that. Very important. Now, we certainly can't graph these inequalities until the x is by itself. So we're going to basically do the same thing we did before, to get x by itself. We're going to follow the order of operations backwards. I'm going to get rid of that 7 first by subtracting a 7. Of course, I have to do it to both sides. And I'll have, let's see, 3x is greater than 36. Now I still have to get rid of the 3. He's multiplying, so I'll do the opposite. I'll divide. Of course, I have to do it to both sides. And I'll get x, or 1x, which is the same as x. X is greater than 12.
The important thing is it your final answer?
Well, if we ask you to solve it, it is the final answer. But if we asked you to solve and graph it, you've got to draw the picture. At least a line like this, and at least a 12. Okay, maybe some other numbers too, but at least a 12. Now this one is not or equal to, so we're going to just have a circle and go to the right, because those are all the values that are greater than 12. Got the idea? Now I need to tell you, there is one difference with inequalities from solving regular equalities. And I want to demonstrate it to you. Now we know 4 is less than 8.
You are correct, sir.
Now, if I add 2 to both sides, that seems fair, doesn't it? Add 2 to both sides, I'll get a 6 and a 10. And note that 6 is less than 10. Big deal.
You're absolutely correct.
Well, we were fair. We did the same thing to both sides. What if I multiply both sides by 2? I'll get a 12 and a 20, won't I? And 12 is less than 20. Nothing crazy going on there.
You are correct, sir.
Well, now I'm going to try dividing both sides by negative 4. Now pay attention. 12 divided by negative 4 is negative 3, and 20 divided by negative 4 is negative 5. Is negative 3 less than negative 5? Picture it on the number line.
Wait a minute.
It isn't. It isn't. Negative 3 is bigger than negative 5.
There's something wrong with us. Something very, very wrong.
It seems weird, doesn't it? I was as fair as could be. I divided both sides by negative 4, and the truth got lost here, didn't it?
Oh, right, guys.
Well, what you're going to have to remember is, if you divide or multiply both sides by a negative in an inequality, you're going to have to switch the sign. That's the one difference. If you divide, and probably division is be what you're doing, if you divide both sides by a negative, then you'll have to switch the sign to keep the truth. Let's try one. Well, in this problem, the first thing I'm going to do, as I always did, was get like terms together that are on the same side. And they just combine, don't they?
I know that, dude.
Okay, now, things that are on different sides, we can't combine them. We're going to have to basically kill them. I'm going to try and get rid of this 3z by subtracting a 3z from both sides. Now, negative 2 and negative 3, don't forget, make negative 5. Now, keep your eye on the z. Who's keeping the z from being alone? The 37 isn't bothering you at all. Got to get rid of that 7. So I'll subtract 7 from both sides. And then I have to get rid of the negative 5. Now the negative 5 is multiplying, so I will, I'm going to have to divide by a negative. Of course, if I do it on that side, I have to do it on this side. Now when I divide by a negative, I have to flip the sign. We just showed you that. So I'll get z, this time, is less than negative 6.
Yeah, baby. Yeah.
So you'll have to remember that when solving inequalities. Now,
Wait a minute, 99. That gives me an idea.
there is another approach to this type of an equation, so you won't have to remember that quite as often. We can still begin the same problem by combining like terms, but instead of subtracting a 3z from both sides, how about adding a 2z to both sides. Watch what happens here. I'll have 1z on the 5z over on the right side. Now who's bothering the z? Now the 37 is a problem. And I'll subtract him from both sides. Now I'll be dividing by 5. I won't be dividing by a negative. Of course, I have to do it to both sides. But I will not switch the sign in this case, because I didn't divide by a negative. Now, there was a negative there, but I didn't divide by a negative, so I don't flip the sign. And the answer in this case, of course, is the same. You have to read the letter first. I know negative 6 is greater than z, but I'm graphing the variable, so I should read the variable first. And this would actually be read, z is less than negative 6. The variable is what you're interested in. So my secret is this. When you have two variables, always pick on the little guy. Okay? If you mess with the littler one, you'll never get a negative and you won't have to worry about switching the sign. Okay? And, of course, always read the variable first once you have the variable by itself. Very important. Okay? Okay, go try that homework. Dig in.